Okay. So thank you for the award. Here I present the work that we did. I did jointly with Uri, that is here, and Tomer Koren. The dimension strikes back with gradients, generalization of gradient methods in stochastic convex optimization. So this work discusses generalization in machine learning. Of course, as you know, generalization is the ability of models to perform well on unseen data beyond the training set. If the training set was sampled from a distribution D and the performance is measured by a loss function f, we are interested in minimize the test error, which is the expected loss with respect to the distribution D. And two other objectives that I will mention in this work are the test error, the train error, which is the average loss with respect to the examples in the training set, and the generalization gap, which is the difference of both. So classical studies which discuss generalization actually discuss properties of the learning problem. They show that if the learning problem satisfies certain properties, they all algorithms generalize well, or ERM generalize well. Such properties can be low VC dimension, uniform convergences, and many more that were presented in this conference in particular. However, we know that in modern scenarios like deep neural networks, the generalization depends on the algorithm. If we use particular ERM, arbitrary ERM may perform poorly, but if we train with gradient methods, most of the times the algorithm will output models that generalize well. Motivated by this, there are two approaches for establishing generalization. The first one is algorithmic independent bounds, like uniform convergence. For this, we first bound the generalization gap using uniform convergence or any other algorithmic independent bound. Then we use a bound for the train error and use the sum of train error and generalization gap to bound the test error. Another approach for establishing generalization is algorithmic dependent. I mentioned two here, but there are many more. For example, implicit bias of gradient methods is the belief that gradient methods converge to simple models that generalize well. There can be many properties of simplicity, like low norm, low rank, maximal margin, etc., etc. And algorithmic stability, which is the change of the output of the algorithm when you replace one sample in the training set. And for using such algorithmic independent bound for showing generalization, you can bound the generalization gap and train error on the set of likely outputs, and in such a way bound the test error. So in this work, our motivation is to discuss the relevance of the approaches I showed before in the setting of stochastic convex optimization. There are two reasons why we consider the setting of stochastic convex optimization. One, this is a very fundamental setup when we can say rigorous statements there, and the assumptions are minimal. The loss functions are assumed only bit, convex, and Lifshitz. And already in this setting, interesting phenomenon happens. For example, the generalization in SCO, in stochastic convex optimization, depends on the algorithm. SDG generalizes optimally, but ERM, arbitrary ERM, may perform badly when the dimension is larger than the number of examples in the training set. Particularly, we want to discuss the relevance of this approach in gradient methods. We actually discussed two gradient methods in this work. The first one is gradient descent, where in each iteration we make a gradient step with respect to the train error. A classical result shows that this algorithm minimizes the train error. And the second algorithm is SGD, when in every iteration, we sample a new example from the distribution and make a gradient step with respect to the corresponding loss. And the classical result showed that this algorithm minimized the test error. And our results are the follows. The first one, we have a result for gradient descent, and we show that we actually construct a SEO problem in dimension d equals n squared, such that with constant probability, although gradient descent minimizes the train error, the test error and generalization gap of gradient descent are constant. I mean, gradient descent does not converge at all with respect to the test error. And this show that gradient descent, this translates to a square root of d lower bound for the sample complexity of gradient descent. And this is the first non-trivial dimension dependence lower bound for the algorithm. Exponential improvement on previous work, which showed the logarithmic lower bound. Here, there is a follow-up work of Livni that characterized the exact sample complexity by d. Another result, before another result, as you can see here, this is an illustration of the error of gradient descent. The train error is minimized to 0. However, the test and the generalization gap increases and reaches a constant in the end of training phase. Another result that we have here is for SGD. Using the same construction technique, we show that although SGD minimizes the test error, the train error and generalization gap of SGD are constant after the training phase. This is pretty surprising since the training error is represents the examples that the algorithm did see that during the training phase. So on the examples the algorithm saw, the model performed badly when you take average of all the losses. Again, this translates to a square root of the empirical sample complexity lower bound and non-trivial dimension dependence, an exponential improvement of previous work. Here, this is still a particular question whether this bound can be improved to a linear lower bound. As in GD, but differently, here the test loss decreases to 0 during the training phase, but the train error became larger. What it is mean? What can we conclude? That if we use this approach for bounding the test error of SGD, we get a very vacuous bound Y, because the test error is small. However, this side, the right-hand side, is very large, since the train error is very large and the generalization gap is very large. So the sum of them gives a very vacuous bound for the test error of SGD. And a conclusion of that is that any generalization theory of SGD cannot go through bounding generalization gap and train error. I mean, any approach that I showed before, like uniform convergence, algorithmic stability, will not work for SGD in stochastic convex optimization. Another discussion that I want to have here is the discussion of implicit bias in stochastic convex optimization. Implicit bias, as I said before, it's the belief that the model the algorithm converges to simple models with a small generalization gap. So here we saw already that the algorithm converges to a model with a large generalization gap, even constant. However, the algorithms does not, here, the algorithm do not converge also to models that satisfy simple rules, like no norm, no margin, and any rule I mentioned before. Actually, the models in our construction memorize the training set. The whole training set is encoded into the iterate of the algorithm. And this memorization happens even in the most fundamental setting of SEO for the most canonical learning algorithms. Let's summarize. First, we showed that the algorithm, the generalization in SEO depends on the algorithm, while SGD generalize optimally. Other gradient methods like GD may perform poorly in the overparameterized regime, which the overparameterized regime is a setting with a large relevance in practice. Another result that we have here is that the generalization of SGD cannot go through the conventional approach of bounding the train error and the generalization gap and use the sum of both to bound the test error. And we also showed that are many senses of implicit bias that do not hold in stochastic convex optimization for popular gradient methods like gradient descent and stochastic gradient descent. Thank you very much.
So we actually have time for a few questions.
Thanks, great talk. Can you explain more what it means to memorize the data set in the SGD case, but have large training error?
That is mean that if you see the iterate, it is very complicated iterate, but you or the gradient oracle can say what example were in the training set and what examples were not in the training set.
I see. So there's public knowledge about all the possible examples, and just by observing this information, you're allowed to pick out which one the gradient came from.
Yeah.
Okay, thanks.
So when you were showing the generalization bound was bad, what kind of functions were you using? Like, were they convex, non-convex?
Convex and Lifshitz.
Convex and Lifshitz.
Yeah. The minimal assumption, like even in the convex case, gradient descent may overfit.
Okay.
That is what.
Is it the case that in your setting, if you assume that the optimal parameters are bounded, that you would get a provable convergence rate?
For gradient descent, this happened only even in the bounding regime when you, for projected gradient descent, when you in the unit ball, our result holds there.
Okay.
Could you just clarify what you mean by the train error in the SGD case? Because you're saying you run it for T steps. Is there a fixed training set, or?
The training error is as I mentioned here, is the average loss for all examples that were sampled from the distribution.
Okay, so when you run it for T steps, it's then all of the iterates that you've seen so far.
Yeah.
Is that okay?
That is what's surprising, that the STD, when you take the average loss of all the examples that the algorithm did, so during the training phase, it's performed poorly.
Okay. Thank you.